The concept of robots and machines being able to see the world around them has been the promise of science fiction that has now become a well understood reality. From vehicles to industrial equipment, users have begun to expect our systems to recognize and react to the objects around them based on visual interpretation. As engineers, we often rely on more complex processors to do this in our designs, but is the microcontroller catching up and able to meet the needs of sophisticated machine vision? Okay, I'll admit it. A big part of the reason that I'm an engineer today, I think probably is because as a kid, I loved Star Wars and Star Trek and the Terminator movies and pretty much anything that had a robot in it absolutely fascinated me. And the potential for the ability to own a system or some machine that could actually work around my life and the world around me absolutely fascinated me, and I wanted to be part of that. I remember, and now I'm really dating myself, being about 7 or 8 years old and getting a Boy's Life magazine in the mail and seeing an article in there where I could make my own R2D2 robot, and I was so excited. I poured through that article for hours trying to figure out how I could do this at home and have my own droid. And pretty quickly, as I was reading through it, I realized all I was going to end up with was a blue and white upside down trash can sitting on some vacuum cleaner motors. And it wasn't going to be able to interact with me or the world around it at all, just would kind of roll around my garage. And I got pretty dissuaded. Today, though, we see so much going on in the way of sensors and image sensors being able to create machine vision and create machines that can react to the world around them. I think my 8-year-old self would be pretty giddy about what's possible. And beyond that, our designs just a few years ago really required a pretty sophisticated microprocessor that's power hungry, expensive in order to do that level of machine vision. But just recently, we've seen microcontrollers come so far in their capabilities that now we can do machine vision in much lower cost, much lower power consumption type applications that I think is going to open up this space in tremendous, tremendous ways. Today, I have the privilege of speaking with Louis Gobin, who's the product marketing engineer of AI solutions at STMicro, and an expert in this area and some of the developments that we're seeing. Louis, thanks so much for joining me on The Current today.
Thanks for having me, Ted.
Yeah, really excited about this conversation. And I've seen some of the new products that ST's come out with. Particularly, I know we're going to talk today a lot about the new microcontroller series, the STM32N6, which I think is a real game changer in this space. But I've seen a lot of machine vision applications for quite some time using, again, more of the Cortex-A type devices or even feeding image data up into a server or to a more sophisticated computer to do things like facial recognition, human detection, and stuff like that. We've seen these Cortex-M start to make some real headway in this space. What advances have really made that possible for microcontrollers to start to really supplant what microprocessors have been doing for machine vision?
Yeah, no, you're absolutely right. That new generation is changing things and changing what can be done. But to give maybe everyone the same baseline, machine vision was possible on microcontroller even a couple of years ago. So we have a good example. I'm going to use an ST reference. Sorry, that's my world. But,
Of course.
The STM32H7, for example,
Yeah.
we were able to run a vision application where we find people in the image, in frame, fed from a video camera, and just detect them, put a box around them. And that was running on an STM32H7, and it was a model that was constrained by the RAM available, but we were able to make it run at about 3.3 frames per second. So it's not real time, but it can be useful. It was a small model. But now with the STM32N6, to give kind of the leap that happened in what seems like a few months or a couple of years just, we're running the exact same model, doing the same thing, so a little bit underutilizing maybe the N6, but we're running it at 300 inference per second.
Wow. So 100 times improvement.
We're not playing in the same, never mind world, we're not playing in the same universe at that point.
Right.
It really is a jump forward. And so to actually, answer the question, what really makes this possible is, I think, a combination of IP. First of all, the neural processing unit, the AI accelerator, however you end up calling it. Obviously, that's a core. That's what's going to take the heavy load of the compute. But being able to make use of it, being able to feed it data, being able to then display the result, really is part of the application. People don't just run a model and then don't do anything with it. You want it to interact with the world. That's the whole point of it, is to adapt. And so it has to ingest data, and we have a vision pipeline on top of it with a image signal processing available on it. We have big RAM. We put 4.2 megs of RAM on this to fit the model, but also to fit the image stream that you're going to be using. So we have the STM32N6, which is demonstrated and honestly very, very good at AI. That's still a general microcontroller. I don't want to give a false impression, but I think it's important to have those abilities of adapting to the world, interacting, genuinely running complex vision models on what's around you with the application that goes with it. So we have kind of the hyperf graphics that goes with it that lets you actually display on a small, large, medium screen in real time what you're using without bottlenecking the microcontroller, because machine learning doesn't replace everything yet. So you still have the rest of your stack of decision making, of communication to run somewhere, and that's on the microcontroller. So it kind of makes the N6 is kind of that general purpose micro with the possibility of running live AI or real-time vision machine learning on it, vision AI, however you want to call it. But I think the real advance is not only the neural processing unit is a core of it, but also a better understanding of what we need, all of us, for those applications, and have put the brick of the puzzle together.
Right. No question. And I think that what you've done there to kind of put all those pieces of the puzzle together is really started to blur the lines for engineers as to when do I select an MCU versus when I select a microprocessor for my application. What are the considerations that you think engineers should take into account for that?
Yeah, that's a good question, and one we've already had to ask ourselves, honestly.
Yeah, right.
And I think the answer is actually similar to what I said above, in the sense that we are going through a very similar decision process to what you would do for microcontroller versus microprocessor right now, or just before this, for general purpose application. The calculus is going to be around, so what do you need? Do you want to run Linux on it? Do you need to run Linux? What kind of general purpose processing are you going to need? If you need 4 Cortex A's just to run your base stack, that's not a microcontroller, however you want to call it or package it.
Yeah.
If you're looking specifically for computer vision applications, the calculus is still very similar, but with the new capabilities. So if you're looking for real-time vision on a microcontroller, so that means lower power, that means lower cost, that means not having to worry about heat dissipation in that case, then looking at the microcontroller solution kind of still makes sense. It's just that now the applications you can put into your microcontroller checkbox basket includes real-time computer vision.
Right. That's, I think, absolutely incredible. And I think that really is what it comes down to, is how much do you need that processor to handle? If it's only doing the machine vision, I think you're getting to a point where a microcontroller probably can do it for you. If you're doing a bunch of other applications, you need a bunch of threads, yeah, you probably need to stay in a microprocessor, and that certainly makes sense. From your perspective, are you seeing new applications and new products starting to really embrace this and move to the microcontroller? Do you think it's really going to open up an entire new space for machine vision that maybe hasn't existed historically?
So let me visit what we talk about historically, maybe. So
Okay.
5 years ago, we had customers that had AI advanced research teams, basically, that were showing off internally and even publicly projects that were doing live AI solutions that were really impressive, that everyone kind of wanted to see go to the market, including their own sales team.
Right.
And the problem with that was the hardware it was running on. It was just too expensive, not only in dollar tags, but in power consumption, in heat dissipation. It was not the idea was very viable. Everyone wanted it, but it was not a viable product for the market. So I think what we have around smart city, especially, I'm thinking this is what really comes up, smart buildings as well. we had use cases, examples, but deployment at scale kind of hasn't taken off yet, and we think it's because of cost. There is a cost, the power budget, the footprint, the heat, the usual cost associated with big, bulky computing solution at the edge. And I'm hoping that the STM32N6 is changing the calculus really for those to make it kind of a mass market type of application, leading the way for those to be so the application that we already knew we wanted, all of us, but kind of didn't make sense to have yet. And so we have that possibility, and that extends to that plays on the strength of the microcontroller. We have a microcontroller that's qualified up to 125 Celsius, so industrial environments are included. We kind of maybe not invented a whole new set of applications, but broke down the barriers to access, as well as kind of expanded the scope of where it could be done.
Right.
And that's, yeah, I think that's really the difference that we have with this, is that something snappy, new, and efficient.
Right. Yeah, and it certainly is that. I think a big part of the reason I wanted to have this conversation and wanted to invite you on the program is having myself seen it at Embedded World Austin back in, I think, the November timeframe, and seeing the N6 behind closed doors. It was very under lock and key at that time. But looking at a microcontroller that could track my movements, could track my fingers, can track my face in real time. I'd seen microcontrollers, to your point, that did, yes, you could do 3 frames a second and things along those lines and track things, but the fluidity in a microcontroller blew my mind. The power consumption, you could go up and touch the chip and it was cool as a cucumber. And then also seeing the price points that we're seeing out of the STM32N6 beyond that really just kind of blew my mind that all of this was capable inside of a microcontroller. And I always hate for any episode of The Current to become an advertisement or anything like that. I want to talk from the engineering perspective, but it really is impressive what you guys have built into this one chip. What is it that is really ST has done inside that chip to enable such powerful real-time image processing for the machine vision applications at such low power and low cost?
I think it's really centered around that philosophy of having a general purpose microcontroller, something that, sorry for the ad, ST has been doing for a while. We know how to do it. We know how to do it well. And so we took that and added the bricks that were missing, once again, from return of experience.
Sure.
And so that's the NPU, so the neural processing unit, neural art, however we end up calling it. That is not just an accelerator, it's an STIP that has enough internal memory so that we don't have the traditional having to query external memory all the time for data that's going to be reused, for example, the weights. So we try to take the knowledge that we all have of the standard von Neumann architecture and minimize the problems that come with it specifically for machine learning applications. So that meant an NPU that was kind of self-sustained. That meant having a dedicated GPU, a dedicated image signal processing unit. So we wanted to offload as much as possible the microcontroller because, once again, nothing new. You can run dedicated software on general purpose hardware, and that runs. But if you can run it on dedicated hardware, you have huge gains. The question is, do you run it enough for it to be viable? And now we see there is enough of a market, there is enough of a range of applications in vision, in real-time visions, in real-time AI processing on microcontroller for the answer to be yes.
Right.
And I think the ISP is a really good example of that in the sense that we wanted something that would offload kind of the main things that were asked for what the data coming in that case, images. Those are the heaviest processing to do. And that also gives us a lot of flexibility on how to plug in a camera, what camera you can select to plug in on the N6.
Right.
Yeah.
Yeah, and I think, so that adds another layer of complexity, I think, for the embedded design for the engineer is, now I'm good. I'm going to go with the STM32N6 for my microcontroller. Now I've got to select what camera is the right fit for me. What are some of the different peripherals that you guys make available inside the N6 for camera selection for engineers?
Yeah. So I think the first one is going to be the MIPI CSI2. So two-lane interface for the camera. That's what we support. We support MIPI CSI2. So that means using the camera that you need for it.
Right.
If you need something advanced, something specific, some specific subtype of camera that does near infrared, for example, that's up to you.
Right.
We have so audio is also a big one that we wanted to be able to address either in combination with vision or completely independently. So MDF is one of the input for audio that we have. We have a lot of memory interface around Exaspy, Octospy. It's a flashless device. Sorry, I kind of didn't mention it before, but
Right.
we have a lot of RAM, but also a flashless device because we see such a range of application that we're not going to come out with like 50 parts covering all of it.
Right.
So more use what you need kind of approach. We have the gigabit internet with time-sensitive networks, so trying to address maybe not only general like mass market consumer applications, but also not stray too far from the STM32 DNA of general purpose applications, including industrial. And with TSN, you're able to not only address industrial, but also a new market we think is coming up, we see coming up, are robotics applications. And those have kind of a mix of requirements between consumer and industrial needs. And then usual I2C, I3C, USB, all of that is stacked on top. But it's not just an NPU with on which we slapped a Cortex-M and called it an MCU solution. It really is a general purpose microcontroller with that ability of generalizing. So to come back to your initial question, MIPI CSI limitations is around 5 megapixel, but we support obviously SD cameras, but generally we support cameras that can interface with it.
Yeah.
And the dev kits, I mean, come with demo and project that support those cameras specifically, but it's not close to anything else. Yeah.
Right. No, and the dev kits are very impressive. I think, really complete solution you can do a great proof of concept on. So that I think is very helpful in engineers as well. And the flexibility just with those peripherals to really then be able to go out and select the right camera for your application, I think is very, very powerful as well. And the challenge I think sometimes resides in the tools. Beyond that is, are the drivers for my camera available for this particular microcontroller and things like that? That's something I think that's got to exist. And I think that gets into some of the complexity in any machine vision system or really any AI ML in an embedded design is the tool set. How do we make that easier for the engineers to actually do their machine learning or embedded vision application? What tools does ST make available, whether it be drivers for cameras or whether it be the actual tool set to develop your models and things along those lines? What has ST built there for that ecosystem?
Absolutely. I'm going to go back once again to the history part of this,
Sure.
because I've done AI for ST for my whole time at ST, and ST has not waited for the last year and a half to jump into the AI game. So
Yeah.
I think from memory, the first AI tools at ST came out about 5 years ago. Internally, we've had projects around AI and building on AI, either for ourselves or generally, for the past decade. Like it's not something new. There is expertise, there is knowledge, not just as, hey, can we make something for developers, but as users ourselves. We've used those tools. We needed to implement on microcontrollers those solutions. So we started creating that ecosystem, and then 5 years ago, it kind of came out and became public. So not going to go through it. We have a whole ecosystem AI page that kind of summarizes everything. If people are interested, you'll find it online easily. But all of it is in STH AI Suite, and that goes from having sensors with AI acceleration all the way to the microcontrollers, the microprocessors, as well as all the software that goes with it to use it, because we started with doing machine learning on general purpose STM32s. We still do it. It's one of our main range of application for machine learning, and that's exactly as you said. That meant having the tools to either create the algorithms or let people developing the algorithms implement them on the microcontroller. And I'm just going to address one of the tools, Developer Cloud, because I think it's the one that speaks best to what the teams that are trying to do AI on the microcontroller are going to be confronted with. So it's a tool that's been really popular because I come from a background of data science, honestly. Didn't know much about microcontrollers until a few years ago. And the developer cloud kind of take that approach. If you're a data scientist, you're developing for an embedded application, you can upload your model, you can compile it for the microcontroller, you can test it on that microcontroller without having to program anything. You get to see what kind of footprint it has, where does it live, footprint per layer of the model, as well as inference time per layer. It supports quantized, non-quantized, mixed quantization model. Sorry, for those that is meaningful information. And the goal really was to bridge the gap between that AI data science team, which is not necessarily familiar and definitely doesn't have all the tools for microcontroller programming, and then the embedded developers. Because at the end of that process, that loop that's kind of focused on the AI team, what comes out of it is C code.
Right.
C code that you can take, you can embed as is, you can play with it, you can modify it, you can read through it, understand it. The goal really is to make that bridge between those two components that have now become part of the development pipeline of creating the actual algorithm from implementing it, embedding it. And there is not one without the other. I know the hype is around AI right now, but it's one of those things. It's very nice to think about it, but if you can't have it on the device, it's a nice thought. That's it.
Right.
And I think that's a little bit of the philosophy around those tools is really we're not going to replace data scientists. We don't replace embedded developers. It doesn't really make sense.
Right.
We're just here to give the tools to program the device to make it happen.
Right. No, and I think that's one of the strengths that you guys have had for a long time at ST is the ecosystem that you build around to make it very, very easy for engineers. And I remember, I think 4 or 5 years ago at CES meeting, I think one of your partners, Cartesium, that you guys ended up acquiring to do a lot of your machine learning and AI type of things that I think has really given you guys that footprint, that power, and really that credibility in the AI ML space for engineers to design with your product and feel comfortable that there is an ecosystem around it. It's not going to be a situation where the software company's saying it's ST's fault, ST's saying it's the software company's fault. No, you guys own both sides. And so you end up in a situation where engineers can go to one place to work through any issues that they may have as they're working on their designs, which is absolutely incredible to speed things up.
No, absolutely. And I was part of Cartesium before the acquisition, so I'm biased, and thank you for bringing it up. I appreciate it. But I have to say, ST did this as kind of a multiple approach thing because CubeAI also existed already at that time. So that idea of letting people not just create easily the algorithm, but have a specialized team be able to embed the algorithm on general purpose STM32 was already there and is still here now. So I hope that Cartesium added benefits for the embedded developers specifically working on STM32, but in general, it really is that idea of what did we need as ST to make it work, and so if we needed it, everyone else programming for it probably does as well.
Right, and no question. And I think we've started getting a lot familiar with the Cartesium tools, with more of, just a lot of sensor inputs and, taking a lot of sensors to understand that, hey, this vibration pattern and this humidity and this temperature mean that I've got a ball bearing going out in my motor and I need to roll a truck, things like that. And I think it's expanded so much more now in the capabilities and the things that we can do now that we're adding machine vision into it. So very exciting stuff. And so, Louis, thank you so much for joining me today and kind of sharing some of your experience and the direction that things are going. Again, I always hate for any of these to end up feeling like a commercial for any one product because I want to talk just about machine vision, but I do think ST's really built an amazing solution here with the STM32N6. To our audience, thank you so much for joining us today and learning a little bit more with us about what's going on in the area of machine vision in microcontrollers. If you have interest in this, if you're working on a project where you want to implement machine vision, you're trying to make a decision between microcontrollers and microprocessors, we would absolutely love to help you with that. We have engineers all around the world that can help you make decisions on what your design should look like, help architect that out, and also certainly bring in demonstration boards, eval tools, and everything so you can make the best possible engineering decision for your design. We'd be happy to do that. Please reach out to us at Shaping the Future. That's one word, Shaping the Future at futureelectronics.com. And we would be happy to reach out to you, sit down with you, and help you in any way that we can be successful in your designs and accelerate those onto production. Thank you again so much for joining us on The Current, and we'll look forward to seeing you next time.